Good evening. My goal tonight is to introduce you to brain-inspired computing, at least from the perspective of my group here at UT. Our computing system, what our goal is massive parallelism, to consume very little power, and to do things that you don't typically do with a PC. We are brain-inspired, but we are not necessarily building artificial brains. So we don't want to build the Terminator. But if you consider those old movies, Arnold's brain was originally a computer chip. It was hardware. Later, they thought about it as software. If you take nothing away from this, it has to be both hardware, software, not one or the other. So what of that hardware? I'll spend some time talking about that. The brain consists of about 1 billion neurons, and even Arnold's brain has about 100 billion synapses. So you need small devices or nanotechnology to realize a system at that scale, at the scale of a human brain, especially using solid-state electronics. The nanoscale devices we're exploring here for brain-inspired computing is the memristor, or memory resistor. This nano device acts as a variable resistor, or for our purposes, as an artificial synapse, meaning it can be trained for weaker or stronger connections that basically form the memory and functionality in our system. As an example of a memristor, we're utilizing hafnium oxide devices that are fabricated by collaborators at New York. You can see some small cross-section of memristor here. We are actually integrating these devices into a full-scale system we're currently designing that will be fabricated sometime in the next year. This system features configurable hardware that can be initialized for different applications. It's also a dynamic adaptation or learning that leverages the ability of the memristor to change state during runtime, and simple models for neurons and synapses that allow for high density and low power operation. A typical memristive neural circuit consists of several things. So we have several synapses driving each neuron. The little triangles at the bottom will be artificial neurons. And if you look at another equation on the right, basically it's just saying if we have the sum of these inputs is greater than some threshold, we'll fire, otherwise it stays as it is. And this is how we form our logic. We can train that logic using several methods. For example, if we supply an expected response over several cycles, the system will train to match those expectations. You can see with the waveforms in red up on the top. This occurs as the memristive values or weights are adapted incrementally over time. And that's the memristive change on the bottom. To further illustrate how we organize these memristive neural networks, one thing we think about as well is we have these two terminal devices. We can organize these into very dense grids or crossbar arrays. And here, each cross-section is actually our memristor, a little square wave-looking thing where the inputs are coming in from the left and outputs are coming down to the bottom. An example application using this structure is a brain in a box. It consists of two of those memristive crossbar arrays. And we've actually trained this one to recognize the letter A, lowercase a, and the fast one wins. So you can see the simulation result where the A was actually faster for this particular network. Our group isn't building Arnold's brain, but we are building what we call Mr. Dana. Mr. Dana is a system that has all the features that I mentioned thus far. It's organized into tiles or cores, so it's a mini-core processor. And each is consistent of many synapses driving a neuron, and we can allow the configuration of arbitrary neural applications. We're in the early stages of the design, so we use simple tests to test this out. You can recognize the triangle against all these other shapes. We're designing Mr. Dana systems that can do this as well. So we have a series of pulses for this to represent our triangle. We can see that we get an output expectation there, that we recognize this as a triangle. And you can see the network on the left. And for several different triangles and different shapes that we consider, we get a pretty good accuracy rate for these types of systems. Classification is another application that we think about. So obviously, image recognition. We look at this one, you might recognize this as an iris. Some of you might even be able to figure out what kind of iris it is. We're actually programming or training our Mr. Dana to recognize the iris and the type of iris that we have. So we generate these networks and we load it onto Mr. Dana and we apply them. One thing to note is that the inputs are spiky. So inside of our heads, it's kind of interesting, we are computing in terms of spikes. So everything we see gets translated. Here you can see the sepal length, petal length of spikes. We have a spiky result. which tells us the type of iris this happens to be, and we actually got a correct result. That was kind of exciting. I've mentioned before that the system can be initialized or trained by example. We show flashcards, for example. But Mr. Dana can also adapt dynamically during runtime. Here, if an input, so the top red is an input spike, and it causes the output, we will potentiate, or we will actually increase its strength so we have a stronger connection next time. We're eventually going to fabricate. That's actually a hard thing. But for now, we can actually prototype these using what's called field programmable gate arrays, and our students can play with this for different applications early on. So we have early hardware examples that they're actually building robots with. In addition to that, I mentioned not just hardware, so 20 seconds or less, I'll explain all, no. You also need software. So the point of it is there's lots of software involved. The bottom line is we need software to communicate with Mr. Dana and also to initialize it, to program it essentially. So we have all of this part. It's an entire ecosystem. This is a young project. We're doing a lot moving forward. Software initializes our Mr. Dana, as I mentioned before, but we must find a balance between the offline initialization we do with software and the online training that we allow for using the hardware itself. In summary, we're having fun. We're designing this new neuromorphic system. We have a lot of smiling faces. I hope that means they're happy. You see my collaborators. I'd like to thank Mark Dean, Jim Plank in particular, and Doug Birdwell, and of course all these students. Thank you very much for your time as well.